That's how you said it. Okay, welcome to the final session for the first day of our very exciting conference on the future and search for life beyond the solar system and all great astrophysics with HabWorlds. Is Takahiro Sumi here? Ah, there we are. Okay, so we're going to continue hearing from our international colleagues. And I'm very excited to see in the program that, as you know, we have great international partnership on James Webb and Hubble with ESA and CSA. But for going forward, we're looking to make it even broader than that. And so we're going to hear from our representatives from JAXA on the activities towards HabWorlds. So probably use that. Okay.
How it works? The razor point.
Should be. No. I guess you can just do slides. Turn it off? What? Oh, there's a button on it. Okay.
The power? Is there main power?
Yeah, no, I don't see the power. Oh my gosh, on the other side. Yeah, I'm looking on the wrong side. So.
Okay. Hi, I'm Takahiro Sumi from Osaka University. I was a JAXA representative for the Louvre STDT. I was very enjoyed studying the Louvre with the Julie, Aki, Jason, and some others from this room. And I'm very happy to come back to think about this HabWorld this time. Today I'm gonna talk about a Japanese activity on the HabWorlds. Currently, the JAXA is participating in the Roman, and we'd like to continue such a collaboration to the HabWorld. So first, let me introduce our activity for the Roman first. The JAXA Roman J team is led by the Toru Yamada from JAXA, and I'm the PI. Here is the Japanese contribution package for the Roman. The first is we are conducting the Subaru Roman synergistic survey by using the 100 nights of the Subaru, such as the photosy calibration with the PFS or narrow band or intermediate band filter observation with HSC. And the second is the contribution to the chronograph instrument, providing the polarimetry capability and also the chronograph mask substrate. The third is we are providing the K-band data downlink station in Japan. And the last is we are providing the ground-based micro-lensing data sharing by the more collaboration And also we built a new 1.8 meter prime telescope for the synergistic observation with Roman. So here is a bit detail about the chronograph contributions. So JAXA provided a high precision mask substrate for the chronograph, and the mask has been fabricated by NASA by using the JAXA substrate, and now assembled and tested. And also we provided the polarization unit with Wollaston prism with camera lens like this, and that is delivered to the NASA and assembled and tested. So the Roman have a lot of data, like 700 times more than the HST. So the Roman is using the 3 downlink ground station, NASA's White Suns, ESA New Noche, and JAXA is providing the Misasa 54-meter stations. And that project has been approved by NASA last year, and we are starting to build a receiver with K-band with 250 megabps. So we built a 1.8 new near-infrared wide-field telescope called PRIME in South Africa. This is the first dedicated near-infrared microlensing survey. And also we are conducting the precursor and also the concurrent synergistic observation with Roman. This near-infrared camera has been constructed by the Alexander Kusher in NASA Goddard Space Flight Center by loaning 4H4RG detector and also the Arcadia electronics from the Roman project. So in parallel to the contribution to the Roman, JAXA sent 4 representatives to the SDDT for large-scale mission concept for the decadal survey. So I was the representative for the Louvre SDDT, and Professor Tamura and Sakon was for the HabEx and the origins. And each of us are making a study group for each concept in Japan. And then after the decadal survey, we merged to one group to study for the HabWorlds. And recently, the Science Council of Japan is making a document, so-called Future Academic Advance Initiative, which is listing their recommendation for the future large-scale project. And our proposal for the participation to the HabWorld has been selected, listed in this document. So let me review the current technology development in Japan. First, Professor Matsuo and Dr. Ito from Nagoya University is developing the one-dimensional diffraction limit chronograph. This is the focal plane mask functions. And one key point of this chronograph is they can achieve the high contrast at 1 lambda over d. This is very complementary to the other chronograph. And another point is they can erase the line source in the sky. So they can know the 2 stars at the same time. So they can search the exoplanets for around the binary. So you can see more detail from these references. And here is their experimental verification in the lab. Here is the contrast curve as a function of the off-axis angle. Here is the center of the mask. This red line indicates PSF of the on-axis source. And the blue line is the 1 lambda over the off-axis source. So they achieved the 10 to minus 5 contrast for the laser source, and without no wavefront corrections. And now they have a new idea for the make it broadband, and by using adding the fiber knurling with real plane phase mask. By combining this new idea, they can achieve the 4th order now over the wide wavelength band. So this not going to the sixth order, but they are very complementary to the other sixth order chronograph. So they are also developing the highly stable spectrograph for the HabWorlds. This is basically the densified pupil spectrograph with pupil slicer. This system is very robust against large load aberrations. In the Louvre experiment, they achieved 9 ppm systematic error under the tip-tilt aberration, tip-tilt error of the 0.2 lambda over d. So they can make a compact high dispersion spectrograph with the size of the 700 millimeter. So they can install the other subsystem in the general other spectrograph. So it's compatible with other spectrograph. So next is the Professor Kameda from the Rikkyo University. He's here. And also the Murakami from JAXA. They are developing the UV instruments for 2 missions, the Russian WSO UV and also the Japan's 60 centimeter UV space telescope. So unfortunately, their project for WSO UV has been stopped for various reasons. This Raptor is recently selected one of the candidates for the future JAXA's small missions. So one of the key science for this Raptor is conducting the UV transit spectrograph for studying the exoplanet atmosphere. Please see the Kameda-san's poster for detail and also the talk in the Friday. So they are developing the high efficiency funnel type MCP. So here's the photo. This funnel type MCP is the opening of each pixel is a funnel shape. So it's a wider open area ratio than the conventional MCP. So they achieved they increased the quantum efficiency by factor of 2, up to the 40%, relative to the previous MCP. So for the development for the Habitable Worlds Observatory, they are making a larger format of this funnel MCP, and also planning to make a 3x3 mosaic to enlarge the area. They are also coupling with CMOS to increase the dynamic range and also the spatial resolution. So this is the engineering model developed for the WSO UV spectrograph. So they are also developing the coating. They currently achieved 88% at 130 nanometer, but the goal is more than the 90%. So here is the brazed toroidal grating developed for the WSO UV spectrograph. They achieved 48% at 130 nanometers. So here is the design of the spectrometer for the WSO UV spectrograph and also the Raptor. So the next is the Professor Murakami from Hokkaido University, and also the Nishikawa-san from the Naoje is building the broadband chronograph mask by using the photonic crystal. So here is a photo of the fabricked the photometric crystal phase mask with 3 layers for the broadband, and also the 6th order and 24 sector vortex. They also fabricated the shaped pupil mask for the TMT segment mirror for optimized for the 24 sector vortex, and this is the experimental results. They also designed for the shaped pupil mask for the Louvre A and B. So they are also developing the optical module for the multi-wavelength dark hole. So their science goal is conducting the multi-wavelength photometry in a time series, and then try to map the surface of the exoplanet like this. So currently, they build a prototype and demonstrated the simultaneous two wavelengths dark hole control like this. This is the preliminary results. And they are planning to do the vacuum tests in the future. So here is the summary. JAXA is currently participating in the Roman, and the Japanese community are very interested in and conducting to the technology developments on the Habitable Worlds Observatory. For example, the one-dimensional diffraction-limited chronograph, highly stable spectrograph, funnel type MCP UV coating, broadband chronographic mask, and optical module for the multi-wavelength dark holes. So we are trying to develop these key science technology to strengthen the mission and expanding the science result. Thank you.
Thank you very much, Takahiro. Questions for Takahiro? You mentioned there's going to be a report from JAXA, I think, on recommending future participation or funding. Mm-hmm. What is the time frame for that?
Well, that is the report from the Science Council of the Japan, and not directly related with the funding agency. So we have to keep working on to promoting the projects.
But the Science Council report coming out later.
In a soon, yeah.
Soon.
Yeah.
Okay, cool. Any other questions? Yep.
Aki Berberge, Goddard Space Flight Center. The UV coatings work that you mentioned, that was aluminum mag fluoride. Okay.
Yeah.
Okay, so that coating, correct me if I'm wrong, it cannot go down to 1,000 angstroms, right?
Right. It's 110.
Okay. Is there any work on? Are you guys doing any work on other coatings that could go shorter?
Well, maybe the Kameda-san knows better.
At this moment, our the science target is the hydrogen line and oxygen line and carbon line. So we are optimizing this design for a bit longer. So, but so we know the importance of shorter wavelengths, but so maybe other mission should do it. Thank you.
Okay. Let's thank Takahiro again.
Thank you.
All right. Do you know how to do this? All right. Our next speaker, I believe, is remote, Martin Bergeron for the Canadian Space Agency. Yeah, I see, Martin, you're up there. We're just getting your presentation. Oh, you've got to share yours. Right.
Yeah.
Go ahead.
I'll say a few words, then I'll go into a share modes if you don't mind. Can you hear me well?
Yeah, we can hear you very well. Thank you.
Oh, excellent. Thank you so much for having me this afternoon. This is very exciting. So, Martin Bergeron, I'm the director of the Space Exploration Development Directorate. It's a bit of an odd mix of activities. It covers system engineering and project management for activities, even the Canadian contributions to the ISS, the International Space Stations. We have activities, of course, for the Gateway, the Canadarm3 being considered there also. But more important is all the science directorate aspects in development for space exploration. That includes planetary science. So we have instruments on MSL, for example. We're also eagerly looking forward to receive our samples coming back from asteroid Bennu, back from Osiris-Rex in September. But more important to this community and to this room is the space astronomy portfolio, which is under my. So that's a bit of an unmix. So today it's a very exciting time for me. I really feel like I've heard all the stories of how James Webb came to be and the Canadian contributions came to be out of James Webb, and some visionary scientists in Canada like Simon Liddy and others that really were there and helped materialize, which was really a dream at the time, which was how could Canada contribute, which is a primary mission of such an importance and relevance. And here we are. So I think we're at a point where Canada needs to step up. And I think that's a key message that I have for today. And if you please excuse my poker analogy, we're all in on HW. I think it's a great mission. Lots of potential for Canada. So let me just make sure I share my screen. You should be seeing it up. So that's a bit of a few slides. We're going to be briefly covering a bit of the relevant topic today. So
yep, we see it.
Okay, so for those that don't know, of course, we have a modest yet quite capable Canadian program, a lot of high-quality astronomers and some well-known companies. But currently, we have collaborations out of the following missions, which is, as I mentioned, the James Webb Space Telescope. I'll talk a bit more about that. But what a success! It goes even beyond our expectations. Wildest dream. The instruments worked well, the gather works well. We got so much out of this mission, and really, but now that's happened. It's behind us in a certain sense. You might not as well know that we are also contributing to another UV mission, which is the AstroSat mission launched in 2015. This is led by our Indian colleagues back in ISRO, but Canada did contribute an instrument, a UV imager, out of this. And really, I think the key message also today is that there's a long-standing history of technological know-how and capabilities in ultraviolet imaging in Canada, and that really speaks to the auroral imaging and observations. Really, that was the impetus and drivers for a lot of our contributions going down to today. A very small but dual-use near-Earth observation and surveillance satellite is NEOSat, where we do a bit of astronomy, especially for objects close to the sun, whether they're comets or asteroids, and getting some support for astronomers. We also support the science contributions out of various missions. Really pleased and looking forward for CRISM launch. Congratulations for Euclid, where we're supporting Canadian scientists in a modest way, but still we're highly interested about those science missions. And there's plenty of other missions where we support a Kenyan scientists. Out of the plan, we're looking forward for some discussions on Ariel, so stay tuned there. Of course, this is under the leadership. I'll talk a lot about Castor today because it's a primary component in Canada-led, and also lots of advance on Lightbird and their warm readout electronics. I think we have key capabilities out there. We're really trying to make this happen. So these are part of the plan, and the questions for today, and you know how and when and what we could include to be part of HWO. So looking forward, we have activities very similar to the NASA decadal surveys. We call this the Kenyan Astronomy Long Range Plan, which is really a community-driven, out of the Kenyan Astronomical Society, community-driven 10 years plan. And in there, obviously, you can see the words and the relationships to all of the great science objectives that HWO is gathering. So we have a clear message from our community that this is of interest to us. A second stage, which is now CSA-driven, is the Kenyan Space Exploration Workshop, which was held last year. It takes about a year for us to generate the final report. So currently have a draft reports in our hands that again indicates that the Kenyan community is of high interest with all of the science objective of HWO. So CSCW, as you see, had very similar topical themes as that of the NASA decadal surveys, where we look at all of the great objects in astronomy, whether it's far field or even our own galaxy. So that's more or less the plan. That's the current status. So the question is, let's take a look at some of the other impetus. So obviously, what in my position right now, what I want to do is to build on the Canadian contributions to James Webb. We keep having people, agencies knocking at our door for the great success and looking at how, what else could we contribute into the next mission. So very saddened that we could not contribute to the Nancy, Rome, and Grace missions. And mind you, there are going to be Canadian technologies flying on that mission, but we did not successfully step up and participate and contribute in a more meaningful national approach way. But James Webb is that great enabler, at least for us. So both NIRIS, the near-infrared imager and the spectrometer, is working extremely well, delivering high-quality science. It has brought out René Doyon out of a very prominent role as a PI there on that missions. And perhaps in a sense even more critical is our role in the fine guidance sensor, which is really, this is a mission-critical component of the NASA-led mission. This is a very challenging world to be in, and we're really pleased that it works extremely well. It's critical to every single acquisitions that Webb has to operate in. So Canadian scientists has really stepped up. So yes, from an agency perspective, we can contribute. I think we've delivered, but now the real issue is we're getting the fruit out of it, and it's the participation from the Canadian scientists in a very competitive, open tender, competitive peer-reviewed process where we are seeing Canadian astronomers be able to almost get to the 5% of the time allocation share that we secured to the contributions that I just mentioned. Those are statistics based on the GEO cycle 1 and cycle 2, but also we have guaranteed time observations based on the astronomical contributions. So very successful from a science perspective, but perhaps what went even beyond expectations is just the unprecedented interest in the Canadian media, the general public, whether it's politicians, etc. It's one of the rare cases where we see this. Yes, it's an high-profile, high-end astronomy mission. It's really sciencey, but we really saw the general public embark in all aspects. And so it's a great showcase of science, technology, engineering, mathematics, which is one of the key mandate that we do have. And we certainly hope that HW would have some kind of earth-shattering impact of the like. So that's why we want to wish and to build on the success of that. And I think for me, it makes it so easier to try to define what could be the next contribution and to convince people that we should contribute on it. So we have a gap. Currently, from a narrow Canadian perspective, we have a gap from James Webb to HW. We're not on Roman. We're not on a variety of very successful missions coming up from whether they're from JAXA, they're from ESA. Just on this day, we were not in a position to do so because we've been working essentially for 10 years trying to get what we think is the next step for Canada, which is to move from an instrument contribution to essentially leading a mission which would be of interest to the international community. So we're really up there. It's called CASTOR. It's a Cosmological Advanced Survey Telescope. It's for both optical and UV research. So it's a wide field instrument. It's a 1 meter class of instrument, but it also benefits from the more recent generations of detectors and technology that's accessible to us. So that's such a great instrument for the time domain in astronomy with the wide field, capacity for deep field, and even ultra deep fields. We're trying to match capacity there. So it's our impression, it's a guess that there's going to be a gap in UV optical domain, and we think that we can be right up there with all of the others. There's a ton of great missions coming up in the domain, but really we're trying to step up and to have a Canadian lead there. So what we would hope out of this is that whether we could benefit from technology developments going on the way to HW, or perhaps we could even be a bit of a test bed for some very selected key elements of HW. Maybe that's the best situation where we could get there. So we're in partnerships and in discussions with, of course, ISRO as a prime potential partner, UKSA. We have engaged with NASA to see, and we're working with JPL very closely, of course, in the for UV and for detector technology. So many technologies being considered. So really, in closing, we're working towards what is a Canadian contributions to HBO. So key statement I want to make and emphasize is that this is real clear. It's critical importance, and really we want to participate. So it's being expressed by the Canadian community. It's clearly expressed in the draft 2020-2030 long-range plan. So we're clear guidance there. And the question is, what could this be? And of course, the James Webb models comes to mind there, where we're really, if we're going to get to science, the first thing I want to consider is what kind of science instrument we could contribute. So quite impressed with the JAXA presentation, of course, and they're quite advanced. I think we already have some work to catch up, but we've got great capacities that were developed all the time, and again in ultraviolet, and all sorts of instruments can be considered and matured, I think, in a very timely fashion nonetheless. So the question is really lingering for me. It's not the science instrument. I think that's if invited, that's pretty much a given, but it's whether we would also contribute a mission critical component such as the guider, for example. And I think that's really up for discussion. It has to be considered. But the very least, which I expect, would be just scientific participation and hopefully on a model that could be similar to the ones on James Webb Space Telescope. So from me, on the driving seat for the Canadian contribution, and purse holder, this is what I'm trying to commit, trying to materialize is of course, a Canadian support to Canadian participation to whether it's the white papers or all other, if any other activities where Canadian scientists get selected and get invited to participate. I don't know if there's Canadians sitting in the room, but you're quite welcome to reach out to us. and to discuss how we could better support you to contribute to those early definitions and concepts. And then, starting as of next year, end of this year, starting of next year, really trying to support financially Canadian studies such as for science maturation. So what are the great ideas out there? What are the great scientists? Which science component of the missions could we contribute? And trying to support you through a competitive call of ideas and activities for science maturations. That would lead to concept studies, trying to define a time horizon around 2025. And of course, that's for discussions to make sure that we're aligned, and then ultimately really trying to be at a point where we mature some selected technologies. So that's more or less where we are, and hopefully that would lead to some definitions, negotiations of hopefully a Canadian contribution down the road. So that's really a CSA viewpoint at this point in time. Perhaps we have questions?
Thank you, Martin. Really appreciate that. Any questions for Martin? Yeah, we have two. Hold on.
Hi, thank you. Great talk. Just maybe you mentioned this already in the slides, but how far along is the Castor mission?
So we're more or less ready. We're really ready. The question is, can we secure the funding? So out of the things that have recently happened, we're working really closely with our friends and colleagues from the National Research Council, the Erzberg Astronomy and Astrophysics Research Center, in close collaboration. And I think now we've come to a common understanding that we need to have a joint response to the long-range plan and a bit of a more formal one from the Government of Canada perspective. We have agreed to formulate that and to proceed with what hopefully would be securing the funding for the mission. So we're still within a time horizon where we would want to launch before the 2030s. Is this optimistic? Potentially from a lot of people's viewpoints, but we're still trying to get that. We have developed all of the technologies. We had great investment so far in working also with partners in the UK and in the US, and more or less ready. And what's limiting factor right now is the partnerships and the funding.
So I have a question. This is Lee Feinberg from Goddard. I appreciate your interest in this and also the great job. I just want to say how wonderful it was to collaborate with Canada on the James Webb Space Telescope. So one question for you is, beyond just a science instrument contribution, you were talking about maybe a guider as one possibility. But there's been a lot of talk about the potential for servicing. NASA headquarters today talked about maybe including servicing. Of course, the robotic arm that was used on Hubble to service Hubble was provided by Canada. Would there potentially be interest in Canada in being involved in that part of the mission?
Thank you. It's a great segue. It's a great introduction. We were just having these discussions. And obviously, we've got a bit of a tradition now building these arms and servicing, whether it's on the ISS and in a few years from now on the Gateway, obviously. So it is an open venue if that's where the need is. And that's why I was saying, we need to discuss. There's so many things that we could contribute. The question is, what traction do we have? How much industrial benefits do we get? And how much science it enables? And of course, when we're talking about robotic arms, it does enable certain types of science, but it's very far from astronomy. And so, certainly from my viewpoint, I would rather prefer contributions that would lead to some and support some of the astronomy and the science component. But if it comes to that, we certainly have capabilities, know-how, and capacity to do so.
We want both. How about that?
We want both. I love ambition. Let's be ambitious. And I'm going to need to table something up. But honestly, in the next 3 to 4 years, we've got the funding to support a lot of the activities I've mentioned. But the question is, how and when do we need to step up to, or game for the much larger contribution down the road?
Well, let's thank Martin again. Thank you, Martin. We look forward to future collaboration.
Thank you. All the best. Have a great event. Take care, everyone.
Our next speaker is Teresa Storchi-Bergman, going to be speaking about the Brazilian Space Agency contribution to HabWorlds.
Hello, everybody. I need first to explain my presentation. I was invited by Jason to present a case for AGN with HWO. So this is going to be tomorrow, okay? And then a couple of weeks ago, he said, why don't you talk about Brazil participating in HWO? So I didn't know what to do, and I said, I'll try. And then I contacted our national facility, which is LNA, Laboratório Nacional de Astrofísica, to help me prepare something. So what they did a poll among the community to learn about the interest. So I'm just presenting this poll, okay? Poll. And I realized that I could make a presentation about LNA, our national facility. We participate in Gemini, coordinated by LNA, SOAR telescope in Chile, and LNA also initiated a participation that we now have at the PFS project, Prime Focus Spectrograph as Subaru. So there was a group that they built the fibers. And what else? And in Brazil, we have São Paulo, University of São Paulo, participating in the GMT, Giant Magellan Telescope. So this is our international facilities that I know of. And so I'm just presenting the result of this poll. Okay. Oh, wait, okay. Okay. Yeah. So if I need to talk with our government, I will say this, right? That we are the country to now move to the next step on science, going to space, you know. So because we have stars, constellations, Southern Cross here in the middle. Okay. So, and probably all the stars have planets as well. So we should participate in HWO. Okay. So the result of the poll. So we had answers from 7 institutions from 6 states of Brazil, then plus 3 institutions that I contact personally. So we have like 10 institutions, 9 states, and then well, what else? Also, you know, people responded, mostly researchers and professors, postdocs, and students, and even retired people. So what the statements were, you know, this is frontier science, and this will be a great impact for the Brazilian astronomy. Laboratório Nacional de Astrofísica is improving the instrument building capacity. As I said, they built the fibers for the PFS. And there are other instruments that they build also integral field spectrograph for the SOAR telescope. So they are interested in building parts of instruments as well. But we are in very initial phases of this. So also, if we begin to participate in these initial phases, this is going to be good for improving the competitivity of the scientists when the telescope become a reality. And, you know, who doesn't want to know the answer to these questions? If we are alone in the universe, and this maybe is the goal of this century for the humanity to answer these questions. Are we alone? Are there other habitable worlds there? Okay. And so what are the topics? So there are 2 people that answered the poll. José Dias do Nascimento, he is already in the Science and Technology Definition team. So he's already participating, and there was Diego Souto. There was also this person, Felipe Ribas, that is interested in trans-Neptunian objects. Kepler and Alejandra and their group are interested in white dwarfs. So to white dwarfs, it's important to observe in the UV. So the UV capability is very important for their science. And also astrobiology. And even the galaxy evolution, then we had answered by Tiago Gonçalves, that is interested in galaxy formation evolution, other people in quenched galaxies, star formation history, myself and Hifel and other collaborators of our group, as well as Ardila, Marinello. We are interested in looking at AGN near and far. So these are the topics that we believe can be explored also with HWO. And I think that's it. I just put my group that our team, it's called AGN IFS. So it means AGN Integral Field Spectroscopy. Since the Gemini, we specialize it in studying AGN, and I'm going to talk about it tomorrow, using integral field spectroscopy. So I will argue tomorrow, and begin arguing today, that we want IFUs. I think IFUs are great for a telescope as HWO to study, the AGN and the AGN host, the relation between AGN and the host galaxies at a few hundred parsecs scale resolution. So this will be the point that maybe I'll do tomorrow again. Okay, so we are interested in doing this, and it looks like, this HWO can be also used for galaxy evolution like that, and AGN. Thank you very much.
Thank you, Teresa. Questions for Teresa?
I also realized that I need to contact the Brazilian Space Agency. We have a Brazilian Space Agency. I didn't think about it, but it's next step.
Yeah.
Probably you go with the LNA director, talk with the Brazilian Space Agency, and begin a movement towards our participation in HWO.
Yeah. Oh, we do have a question. Hold on.
Thank you. I'm just curious. This is kind of a broad question that you may not know the answer to, but like ESA has 22 member states. Has South America thought of a South American space agency?
No, we don't have. Yeah, we just have. Each country has its own observatory or facility, whatever, council, but don't have a South American. We have meetings that we do, LARIN is called, Latin American meetings, but not like a project. Well, there is one project that I remember now that was a collaboration with Argentina, Brazil and Argentina, with an antenna from the ALMA antenna. They are doing a project together. I think it's began operations already. It's called Llama.
Okay, well, let's thank Teresa again. Look forward to future collaborations with Brazil. Our next speaker is Carl Stapelfeld. Is he here? There he is. Carl's going to talk about the role of science metrics in the maturation of future great observatories. Light is on.
Oh, it doesn't have your name? Oh, in the box folder. Yeah.
Yeah, well, I sent it in. So I think we're ahead of schedule, right? Yeah. We got it on a memory stick. You want that?
Yeah, let's try that.
It's back up here.
Go grab. Yeah.
Let's see. Oh, no. Usually we have them transfer. Sorry, it's in my pocket. Yeah. The big USB. Yep, there we are. Okay, thanks, guys. So can people hear me well enough with the mask on? Yes. Right, okay, great.
Can people online see the presentation? I just want to make sure. Yeah.
How do I get rid of that? Okay. So hi, everyone. I'm Carl Stoppelfeld. I'm the chief scientist in the NASA Exoplanet Exploration Program based at the office at the Jet Propulsion Laboratory. So I want to tell you today about science metrics. These are tactical things that we want to do during the next few years, I believe. I mean, science has motivated these 3 future great observatories to make sure that they have certain broad capabilities. But now we're going to have to actually settle on some specific designs. So a way of deciding, which design is more performing than another is to establish, through community discussion, science metrics to talk about how well they can execute major programs that we envision for them. And now I'm trying to go down and nothing's happening. Do I have an advance somewhere else?
You're in a PDF file, so
yeah.
Probably the space bar won't work.
Down arrow is not doing it. There we go. So what was that?
I did the same. Basically, I selected the window first.
Oh, that's the problem. All right. So there are major observing programs that we have seen in the past from our great observatories and that we would expect to happen in the future. So you can think of these depending on what your favorite telescope is. So there's all these wide area surveys and deep fields that we've done with our 3 most recent great observatories. There's the early projects for Hubble, like the distance scale project, and the more recent ones about large treasury programs. Spitzer didn't expect to do a lot of phase curve observations when it was designed, but it ended up doing a lot of that in the Warm mission, and so forth and so forth. In the case of the Habitable Worlds Observatory, the largest single project is going to be the survey of nearby habitable zones to see if you can detect rocky exoplanets and characterize their properties. So we don't know what the missions are going to do enough in advance, but there is information in the decadal, there's information in the large mission studies like Louvre and HabEx, enough to identify these large fiducial programs now. So we can talk about how well a certain design executes any one of those projects. So a metric is either how many of a certain kind of observation you're able to achieve with that mission, or if you've got a time limit, how many you can undertake within that time limit. So there's an ultimate performance, and then there's a time-limited performance. And so there are different kinds of yields. You're used to thinking about, in the context of HWO, what's the yield of habitable zone rocky planets, or for characterization. But there are other things that you could put in there too, like how well can you do a time series observation? How well can you survey a certain area? So I think over the next few years, all the individual flagship missions are going to be talking about metrics for the maturation process under GOMAP. So the decadal survey for HWO did give us one metric. They said do 25 habitable zone rocky planets approximately, and then be a transformative facility for general astrophysics. So we have a metric that we need to follow in the implementation of this mission, at least on the exoplanet side. And the metric envisions, spectroscopy, here the example of the Earth through time, the different kinds of features we might hope to see. But you don't necessarily get all of this spectrum at one time. And there are features in the instrumentation that's going to lead to very different performance at different wavelengths. So in a chronograph, there are image speckles. The image speckles will change their brightness with wavelengths. So in the UV, they could be very much brighter for a given path length error. And then in the near infrared, the inner working angle always grows with wavelength in a starlight suppression system, even if it's a star shade. So your ability to see some planets in the near infrared is going to be more difficult. So we're going to need to quantify how well an option for the architecture of HWO can achieve detections and characterizations across the wavelength range. It's not one answer applicable to all wavelengths. So the role in mission maturation here, we're going to have to think about what is the cost options for any different architecture that might be evaluated. What's the technical readiness for it? What's the risk of being able to do the mission? So we're going to be trading those things. We need to have something quantitative to trade them against in terms of the science performance. And so the metrics are useful for that. So the things that might need to be traded that are going to be affected by the metric results. The telescope design with the different parameters that are listed there. The starlight suppression system, the inner and outer working angles, the throughput, the total mission time it takes to do a given survey. So there are tools already established for the exoplanet side of HWO, and I hope will soon be established for the general astrophysics side as well, that can evaluate the performance of the mission if they are given the parameters, a definition of what should be tracked, and that's the metrics. So we want to make the scorecard for how well the many options for the architecture of HWO can do the exoplanet and general astrophysics science. But I think the most important thing is this tactical stuff has to be broadly discussed in the community. I mean, I could go off in a corner by myself and come up with metrics that I liked, okay? And maybe myself and a couple other exoplanet scientists in the audience, we could do that too. But we want the community to come to a common agreement on what are the things that matter that should be tracked in the design process. And so I think that's a large set of discussions. And because I wanted that set of discussions to happen sooner rather than later, that we've already started working on it in the Exoplanet program. So the values of the metric to start out with is it'll show you what's easy and what's hard in terms of the mission science that can be achieved. It lets you iterate on the science requirements. You can get to achievable requirements instead of saying, here's what we must have, and then you discover that you actually can't make that work with a sufficient level of risk. And so the metrics are not science requirements. They reflect the current understanding of science requirements, but they're going to be evolving toward what the final science requirements end up being. Now, the metrics are not a value that you can necessarily say is 100% right. And in the case of habitable zone rocky planets, the big uncertainty factors in calculating a value of the metric, how many you get, are things we've talked about for a long time. What's the level of exozody? What's the eta Earth value and the estimate there? So if you have uncertainties in the metric, all the parameters you have to use to calculate it, you can track those uncertainties, and they point to areas where precursor work could help you get better fidelity in understanding the performance of your mission. And so that can lead to precursor science goals and investigations. I think we've tried to do that in the past year with the precursor science definition process undergone at headquarters. So that kind of things, in addition, if the metrics have uncertainties, did you really model the system well enough? And how well do you understand all the components of the performance? And then lastly, of course, our future mission is going to have lots of little programs, general observer things, medium-sized things. But the most impactful metrics are those that are associated with the largest projects that the mission is going to do. So at some point, you have to decide, I don't want to track the performance too much of the things that are getting too small. Track the metrics associated with your biggest few survey projects. So the biggest survey for HWO, as I said, surveying nearby habitable zones. The decadal request for 25 habitable zones, it's actually not the greatest metric, because with the eta Earth uncertainty in there, you now don't know if you need to survey a huge number of habitable zones if it's low eta Earth, or a small number if it's high eta Earth. So something that's more definitive is to say that there's 100 habitable zones being surveyed. If you say that, you can design a system to achieve that. It's much more uncertain because of eta Earth if you say it has to achieve 25. This mission survey could take half of the total time. That was what Louvre and HabEx postulated in their versions of the mission. And because we mostly know what the most accessible habitable zones are today, we're in a great position to calculate metrics for that habitable zone survey. We know we're going to look, we know how bright the targets are, we know how close the habitable zones are inside. And so here's some figures from the report that Eric Momajek and myself did on a preliminary target list for HWO. And Noah Tuco and Chris Stark have some additional work on this I urge you to look at. So that one metric from the habitable zone rocky planets from the decadal was 25, but they didn't specify the same thing. HabX defined that as characterizing from 300 to 1,000 nanometers. Louvre Report defined it as a spectrum initially near the 940 nanometer water band. And so we have to decide, even on this very basic thing of what is our 25, what are the characterization aspects that go along with that? That needs discussion that I hope the START team will take up urgently. Another thing is on comparative planetology. The decadal survey did not give us any number saying the future mission should detect this many Jupiters or this many mini Neptunes and so forth. So we, the community working through the START team, have an opportunity to define what the level of achievement should be on that. So there's a room for developing additional metrics in the Rocky Planet survey. So here's some figures from the Louvre report that shows for the comparative planetology, the scientists will always want to see this breakdown of all the different yields for all the different planet types and all the different planet temperatures. But this is probably too many metrics to keep track of in the mission design trades. So we're probably going to have to do something more consolidated. What exactly that should be, I don't know, but it should be a subject of discussion. So I hope if nothing else, I'm convincing you that we have a lot to talk about and work through as a community to decide how to measure the success of different HWO options. So to get started with that, we established a little working group on exoplanet science metrics. It's not science metrics. We're not talking about the general astro part. It should have said exoplanet science metrics. And so the group of people listed there are the folks I've been talking to about this, and Eric Mamajek from the EXEP office is also participating. We're trying to answer the question to begin with, what should be the score sheet, for quantifying the productivity of that habitable zone survey for each mission configuration. Now, you can define the metrics without deciding what the value to achieve is. So that's what we're trying to do. We're saying, let's figure out what the definition of a detection is for a mini Neptune that we want to characterize, and not try to focus on the question, how many should the mission characterize? That's for another group. We're just trying to say, what are the rulers that should be used to measure how well the mission does? And so our group is making progress on a group of 6 different metrics in various stages of maturation. And so our idea is to deliver these preliminary metric designs to the START team when they convene in the fall. So we're a head start for START, trying to get the discussion going. And this is up to headquarters, but the way I think about this is that START won't have enough members to consider every topic in detail, so it's going to need to form a lot of subcommittees that involve community members to talk through various things. And so I think we're possibly a model for how START can bring in a community subgroup to talk about these things, and then bring reports to the main committee to decide what to do with them. So I'm just going to end here by saying that here's the list of metrics that we are currently working on. And so these are the ones that the working group members that you saw on the last slide, were most interested in thinking about. So these are not necessarily the most important ones. It's just what our group wanted to start on. And so when we turn this over to the START team, they're going to work to maybe improve on or throw out our metrics if they don't like them. But more importantly, to do the other metrics that are not, that we haven't even touched yet, that still need to be established. And especially that's true for general astrophysics if that community decides that there are big enough programs that would benefit from following this approach. So that's my last slide, Mark. Yeah.
Thank you, Carl. Questions for Carl? Is there anyone on the... Oh, well, let's just read it.
So there was a question from Chris Stark. One of the most difficult aspects of the ExoEarth yield metric was getting folks to agree on how many was enough. That took a decadal study. How do you envision the community deciding on quantitative goals for these metrics?
So repeat the last part.
How do you envision the community deciding on quantitative goals for these metrics?
Well, it's not going to be, up to me, certainly. I think we just have to gather a lot of ideas, a lot of different versions of the metrics, and then debate them back and forth. We don't want to limit and try to have a gate right now that we do or don't like that one. Let's collect the ideas to start with and then start the conversation. I don't know how quickly that can play out. we may be still talking about metrics 5 years from now when we actually have the different architecture options. Is this really the right metric or not? So I think the most important thing is just let's start the conversation.
This isn't really a question for you, Carl, so much as well, it is a question. How do we make sure, that's the question part, that we don't keep doing this so long that we forget what we've done in the past? I think you and I have both seen cases where there was an answer tucked away in chapter 5 of some report and nobody was paying any attention to that anymore. Right. And we just then redid the work, right? Reinvented the wheel. Yeah. Now that we really have a start, how are we, as a general concern, how are we going to make sure we only do these things one more time?
Well, as a veteran of the terrestrial planet finder, as the first, study scientist for the TPF Chronograph, I do feel that a lot of things were not remembered from that stage. And it's not just the mission studies, like Daniel Apai has a whole SAG report about, science for this future mission that I think we didn't look at quite enough, during HabEx and Louvre. So my advice to the START team would be, in your first meeting, let's have a whole rundown of what was accomplished in these previous studies. You can't, if you tried to do the Louvre report at the START meeting, you would be going for 3 days. So it has to be, consolidated down quite a bit. But every generation of astronomers starts making their own set of references to the papers from the past 5 years and doesn't know about the references from 20 years ago as much as they might. Yeah.
Great. Any other questions for Carl? Just a quick thought or comment, which is this is going to be hopefully it's serviceable telescope that's actually serviced. And so my vision for this telescope is that it will be around for 30 to 40 years rather than 5, which is, the primary mission. And so the initial exoplanet survey, I believe, was of order, as you said, 2.5 year survey in the initial. I wonder if the community, the exoplanet community, is thinking about, what the next what you would do after that first survey is done, and how, if there are any metrics there that may come into play, and that might dictate second generation instruments for the
well, there's lots of science targets that were not included in that Louvre or HabEx half-year survey. Yeah. Known radial velocity planets, circumstellar disks, which is my science. So we're not going to run out of stuff anytime soon.
Good. That's cool. Okay. Any other questions for Carl? If not, thank you. Our last word is Aki Roberge from Goddard Space Flight Center, who's going to be talking from science to mission perspectives from the Louvre mission concept study.
Oh, I put up 2. Yeah, that. This one. Yes, it does. Okay, so I'm the last talk of the day. I'm going to try to make this relatively quick. So first of all, I'm Aki Roberge from Goddard Space Flight Center. I'm currently the Associate Director for Technology and Strategy in the Astrophysics Division at Goddard. Sorry, that's really long. But more importantly for this talk, I was the study scientist for the Louvre pre-decadal mission concept study. So I'm going to take a bit of a different approach to what I want to talk to you about from Carl. So, and this talk is really aimed at those people in the audience who are completely new to mission concept development. And it's really my take on the first steps in the process, like how did I get involved in mission concept development in the first place? And so I'm not really going to talk about what the mission-specific science goals are. What I want to talk about is the process of helping you learn how to infuse your science into a mission concept. So, and again, this is my take on it. And this process, it's not rigid. It's not set in stone. There are other very experienced folks in this audience who have, their different perspectives, their different tweaks on this. And I hope we'll hear their insights throughout the week. Okay. So I got into my first mission concept not long after I finished graduate school. And to tell this little story, I made my first and possibly my very last cartoon for a science talk. So here it comes. Get ready. Okay. I'd like to say it was inspired by XKDC, but no, it's just the best I could do. All right. So, at the beginning of this story, I was basically a garden variety observational astronomer. Senior astronomer here, which was actually John Morse, came to my first postdoc advisor there, Alicia Weinberger in purple, and asked her if she wanted to be on the science team for his Horus mission concept. It was a small probe scale UV mission. For one reason or another, she declined, but said like, hey, I don't actually do UV, but my new postdoc does, so why don't you ask her? So there he goes. Okay, asks the question again, and I said, cool, sure. And I really had no idea what I was signing up for when I said that. So this caused me some significant stress at the beginning. But really, thanks to really good preparation on the part of John and his team, it started becoming clear to me what I was supposed to do, what they were expecting of me, and how to get to do it. So what they did is I was given a template for a document called a design reference mission. Now that name really doesn't tell you anything about what it is. But thanks to those section headings and discussions with more experienced members on John's team, I realized kind of what it was. It's an observing proposal for a telescope that doesn't exist. Now, many of us have experience doing observing proposals, so I was like, oh, okay, maybe I can get started here. So I'm just going to go through basically those sections where you start in this in a DRM. Okay, so your first job is to write down your science goal, your burning question that you cannot answer right now because you don't have the observations. And you need to be able to explain why it's important, why it's interesting, and your audience for that is literally anyone, like your grandma, your cousin, your congressperson. And to illustrate what I'm kind of talking about here, I'm using one of the signature science cases from the Louvre study. And I chose one of our two solar system ones because A, I like it, and B, it's relatively straightforward. Okay, so there's your high-level question that hopefully anyone can understand. Okay, then you need to design an experiment that can address all or part of that question. So what do you need to do? The science, so for example here, so in order to, there are many ways you could tackle trying to study how the seeds of the solar system planets came together, but this is the one that we chose. This is the approach we chose to tackle it. And now your audience is scientists outside of your subfield. So they should be able to basically kind of understand how your experiment will address your question, but not really the details, not really check your details. Okay, then now we increase the fidelity again and ask yourself what measurements you actually need to make. So by measurements, I mean properties, like the physical properties of the objects you're studying, like redshift, color, or in this case, size. And you need to get specific. You need to justify the types and numbers of objects that you need to study in order to, give you a scientific constraint. So here we had 30 TNOs with diameters greater than 4 kilometers out to 40 AU to constrain the small end of the size distribution at X precision. And I don't actually know what X is because we didn't quite get there. So this is something that it was like the thing you do in your journal, future work. So, and now the audience is scientists who are in your subfield who can check your assumptions, to check and make sure in detail that these measurements will actually constrain the problem that you set. And then finally, last step, now you really get real. What observations do you need to get those measurements? And that's what it sounds like. but you really need to be able to explain your input assumptions and, most importantly, provide your required exposure time. And again, this audience is scientists in your subfield who are actually going to be able to say, like, 4-kilometer body, 40 AU, that R-band magnitude, that sounds about right. Okay, so here's the first tricky part. So the observatory lies in between the observations you need and the time it takes to get them. And to make that connection, you need an exposure time calculator. So, and that is, it translates the properties of the observatory into observation requirements. Now, those of us who are observers are pretty familiar with exposure time calculators. Probably fewer of us are so familiar with what's under the hood of one. So, for example, you start with your inputs, object flux at some wavelength, required signal-to-noise ratio. That goes into the ETC, and the ETC is basically effectively a parameterized model of the observatory. So it contains things like the effective area, optical elements with their reflectivities, instrument field of view. I could go on and on and on. So ETCs can get very complicated. But fortunately for you, you do not typically have to write your own. So for existing NASA telescopes like Hubble and JWST, there are big teams of scientists and instrumentalists like those here at Space Telescope who provide exposure time calculators for you. On a mission concept study, typically what happens is a few of the more experienced members of the team will produce a streamlined, stripped down ETC, and I'm actually looking at the guy who did it for the Louvre study right there. Thank you, JT. That the whole team can use. And then you get out your outputs, exposure times, number of exposures, what overheads you need, Okay, so that part we can do. So here's the other tricky part. As I said, the observatory doesn't exist. We are trying to figure out what hardware we need to do what science. So all of those observatory properties that are in the ETC, those are variables we actually want to explore in the course of our study here. So for example, like during the Louvre study, we wanted to really understand the impact of aperture size on the whole science portfolio that we were considering, all 12 signature science cases. So, you know, we had Louvre B, we had Louvre A, the big and the really big. So the answer to this is what you actually have to do is you do those calculations again and again and again, varying all of those mission parameters that you might care about. So this is like, for example, what we did for the TNOs that showed basically the sensitivity curves, how small we could get down for Louvre A and for Louvre B as functions of exposure time. And then, and I can't emphasize this enough, also to myself, write it all down. Okay, so this is the 2 pages of the design reference mission document from the Louvre Final Report. The lead was Becky Dawson, who's here somewhere. And looking back at it after 4 years, I realized there were some things we forgot to write down. But Becky is going to give me the info, and I'm going to like put an addendum or something. So she has it. Like some of our input assumptions, like in specific, like we forgot to write down in what albedo we assumed for the TNOs. And then there was that other thing, we did that, you know, future work punt sort of thing at the end there. Future analysis will establish. But still, you know, it's good. You got to write it all down, and write it all down better than we did. Okay, so that's kind of it. That's my parting thoughts. You will probably not be surprised to hear that you will have to do your DRM over and over and over, because there is much iteration is really required to balance the demands of multiple science cases, both on the observatory hardware and on the total mission observing time. But this work is important. Those of you who may recognize some of this stuff, because these questions I laid out, these eventually become the first columns of your science traceability matrix. That's a topic for another time. I am not going to get into it. But maybe even more importantly, this feeds into the mission's most vital, the level 1 mission requirements eventually. So I really want to emphasize that this is important work.
Everybody can contribute to it, even if you're new to mission concept development. And for me, I had a lot of fun when I first getting into mission concept development, because like, think about it, you get to sit down and think about what you do with a telescope that's better than what you have. And this can actually be, for me anyway, it was very enjoyable. And I hope that some of the new people in the audience who are coming to this will also enjoy it too. So that's it.
Thank you very much, Aki. Questions for Aki? One online. Go ahead.
So we have a question from Mark Elovitz. Why was there such a discrepancy between the size of the 15-meter Louvre telescope aperture size recommended by NASA and that recommended by the decadal 6 meters? So why was there such a discrepancy in its size?
Okay, well, does anyone here from the decadal steering committee care to comment? Well, however, one thing. Okay, let me go back for 1 second. The one thing to be cognizant of is that the decadal was very specific about. They said it was twiddle 6-meter inscribed diameter. Now, for segmented telescopes have 2 diameters, the outer diameter and the inscribed diameter. The inscribed diameter, okay, nobody's online is going to be able to see this, but is the diameter of the largest circle you can fit completely inside the primary telescope. So we always talked about Louvre B as being an 8-meter telescope, but its inscribed diameter was actually only 6.7 meters. But as far as, why the decadal made the exact decision they did, you'll have to ask them. Okay.
Any other questions for Aki? I will just second Aki's recommendation. Working on future telescopes is a fun thing to do. So you don't spend all your time on it, but some of it. Then you get tenure, and then you can spend all your time on it. We have another question here. I'll bring the microphone up.
Hi, Allison Youngblood, NASA Goddard. How many DRMs does a mission, like a flagship, have? Like, does it have multiple?
I think that, gosh, well, someone who was there at the early days of JWST will have to answer that one, or the early days Hubble. But I can tell you, like, the way my views on this is that I think that you want to explore, like, a big range, explore a big range of science of what you might do with your telescope. Eventually, those will get prioritized and down-selected to choose what's actually going to be allowed to drive the mission hardware. But I think you want to cast a wide net just so that you know what you can do. So that would be my philosophy on that one.
Maybe I'll ask one online by the time you go there. Yeah. So we have a couple of questions, maybe from Jennifer Sobek. Does a formalized template for the DRM process exist?
No, I don't think it does. I think every team reinvents their own. But it's always approximately kind of like what I said. You start sort of like an observing proposal, which are never identical, right? There's no fixed template for an observing proposal. There's no fixed template for a DRM either, but they're kind of all basically the same.
And second question from her was, are all software development efforts available online?
I assume that is referring to exposure time calculators, perhaps, which JT, I think there was email sent saying that some preliminary exposure time calculators for HabWorlds and the others too? Or just HabWorlds are now available. Yeah, so are available online now. I think there was. Okay, JT will re-up the link in Slack.
Yeah, I was just going to comment. This is Eric Smith from NASA headquarters. Comment on how many DRMs were used for JWST, and I would say literally like thousands of iterations of what eventually distilled over time
Yeah.
into the level 1 requirement. So it starts out, you're iterating
Yeah.
frantically, and then eventually
filter.
requirements
Yeah.
precipitate out, and then all that stops, and the contracts come out.
Yes. Yes, that's true. I should say you won't have to keep redoing your DRM forever. It will stop eventually. Okay. Do we have time? How are we doing?
Right, coming. Hold on.
Okay. Okay, good. Well, that agrees with my expectation then. Yay.
So Gabriel Giono from Space Research Institute in Austria. I was just wondering because, of course, imagining a telescope is very nice, but the science is done by the instruments. And how is this integrated in the process? How do you imagine the instrument as well? And I guess they come from the community, so you have to ask them what ideas they have as well, right?
Yeah, so I think that, let me go back a step. Okay, if I can. Somewhere around here, when you're starting to think about what observations you actually need, that's when you say like, well, okay, I'm going to need an imager, an imaging camera with some kind of field of view. That's when, if it doesn't already exist, you need to either make an exposure time calculator that has that instrument properties in it, or find someone to do it for you. But somewhere in this process is basically, it's going to become obvious to you what instrument you need, and then you go ask for help.
I see, thanks.
Yeah.
Okay, any other questions for Aki? Yes, we do. Hold on. Popular speaker today.
I just wanted to follow up, Aki. I've done this a lot, so I know the pain you're talking about here. But for those interested in this, asking these questions, maybe I put a plug in for NASA has been running the PI Launchpad and the Astrophysics Mission Design School, which are from 1 week to a 10-week activities for early career scientists and engineers to design missions and go through this process in a structured way, best practices. And it could, if you're interested in this kind of thing, the PI Launchpad and the Astrophysics Mission Design School happen typically every year and could be great ways to sort of get involved, practice it, and then put it into action on HabWorlds.
Yeah, that's a good, thank you for that, Jeff. That was a good point. I've heard very good things I've never done the Astrophysics Mission Design School, but I've heard very good things about it. So, yeah, I will second that recommendation.
Yeah, I just wanted to write off that. This is Emily Rickman from ESA STSCI. I did the NASA Astrophysics Mission Design School. Highly recommend. And if anyone wants to speak to me about that, then come find me. I don't think there's anyone else here from the Mission Design School, but be very happy to chat about that.
Yeah, super. Thank you. Okay. All right.
Okay, well, thank you, Aki. Great talk.
Thank you.
Yes, Jason, you have some closing comments?
Yeah, all I wanted to say was thanks again, everybody, for coming and paying attention. Thanks to our speakers for today. Everybody did a great job, except for one. That's a joke. And we'll see you 9 o'clock in the morning right here. That's gonna.
So we give
Carl.